Welcome to iLecture Online. We also have what we call the relativistic correction term. That's this little term at the very back of the equation that needs to be added to the delta TSV. In other words, the difference between the GPS time and the time of the clocks on the satellite. And again, as centered at the center of the transmission on the antenna where the E&M radiation goes radially outward. So the equation for the relativistic correction term is as follows. The change in the time due to the relativistic effects is equal to F times e to the square root of A times the sine of E sub k. Now, what are those things? Well, the first mistake we might make is think that this is the natural number E, 2.718 and so forth, but that's not the one. Turns out that E is actually the eccentricity of the orbit of the satellite, which varies anywhere from 0 to 0.03. As a comparison, the Earth's eccentricity around the Sun currently is roughly 0.0167. So that's the kind of change from a circular orbit that these satellites will have, some slight eccentricity, which of course needs to be taken into account. A is the semi-major axis of the orbital distance from the satellite to the center of the Earth. So we take the square root of that average distance, or the semi-major axis. They put that as an exponent of E, which is the eccentricity of the orbit, and then we multiply that times F. Now, what is F? F is a constant, and it consists of this equation right here. It is equal to -2 times the square root of mu divided by c squared. And that's the number. That's what that is equal to. Now, it turns out that mu is actually the Earth's universal gravitational parameter, and it's the product of the gravitational constant and the mass of the Earth. Now, why do we call it mu? Well, it turns out that we don't know this number all that accurately. We do know the mass of the Earth relatively accurately, but it's better, since we really don't know this number, is to actually, due to the effect of the Earth's gravity on the satellites, we're able to calculate the Earth's universal gravitational parameter rather than try to calculate it like this. So we can get the number directly. You can see that I don't have a lot of significant figures here, but by measurement we can actually get this value very accurately, and it's equal to 3.986005 or 004, depending upon where you get the information, times 10 to the 14th cubic meters divided by second squared. So notice we then take the square root of this number, multiply times -2, and divide it by c squared, where c is indeed the speed of light, so we square that, and that's how we get this number right here. So that's the constant that goes in front of the e to the square root of a. And then we have the sine of E sub k. Now, E sub k is what we call the eccentric anomaly. And that is calculated as follows, and we're not going to go into the details yet, but what this is. But this typically will give you a very small angle called E sub k, and that then gets put into this equation. We take the sine of the small angle, and again you can see, depending upon the size of that angle, the relative effect will be bigger or smaller, and that is of course the orbital effect that we might have due to the relativistic effects, gravity and the speed. Mostly gravity, however, and so later on we'll get into the details of how this is actually calculated. So you can see we take the sine of a small number, which is in itself a small value right here. We multiply it times this quantity right here. The eccentricity, which is a very small number, raised to the square root of the semi-major axis, and we multiply that times this number right here, and that will give us an additional change in the time that we're going to calculate between the GPS time and the satellite time. So you can see a lot goes into trying to calculate that delta, because the better we can estimate that delta and calculate, it's not just estimation, but calculate the difference between the GPS time and the satellite time, the more accurate value we can have for a position of a receiver on the Earth. And that is how it's done.